Okay, we've defined a bunch of operations now on sets, and we've done a little bit about subsets and power sets. It's time to start proving some things about sets. So let's look at a few proofs of some basic things. So along the way, we're going to need to rethink about how maybe we think about a few of those set operations and try to rewrite them in terms of logical statements. So let A and B be sets, then some statements about subsets and equality, intersection, unions, complements, and differences. Let's just tweak them to write them in terms of logical operations. So A as a subset of B, when for all A in A, all X in A, X is also in B, which is the same as saying if X is in A, then X is in B. A is equal to B is the same as saying A is a subset of B and B is a subset of A, which is the same as saying X is in A if and only if X is in B. And these give us ways to turn statements about sets into proofs using some of the ideas that we came across earlier in the course. So union and intersection, X is in the intersection of A and B is the same as X is in A and X is in B. In the union of A and B, it's the same as being in A or being in B. Complement and difference, if X is in A bar, that's the same as X is not in A, which is the same as the negation of the statement X is in A. X is in A minus B is the same as X is in A and X is not in B, which is the same as X is in A and the negation of the statement X is in B. Okay, so this is just tweaking some of these set operations to write them as logical statements. Okay, so let's do a quick simple example. Nice little warm-up. So a subset example. So if we define two sets, let A be the set of integers that are divisible by 6 and B be the set of integers divisible by 2, well then the first set is a subset of the second set. So let's do a little bit of scratch work. So what do we need to prove here? Well, because this is a subset statement, we actually need to prove that if an element is in the first set, then it's in the second set. So it really is an implication, and so we can start by assuming something is in the first set and work our way to showing that it's in the second set. Well, if something's in this first set A, then we know it's divisible by 6. So hence, if A is in A, it's an integer divisible by 6, which means that A is equal to 6 times k for some integer k. Well, we need to show that A is also in the set B, which means we need to show that it's divisible by 2. But since A is equal to 6k, we can write this as 2 times 3k, and so 2 divides A as required. So that's just our scratch work. But really the important point here is we've turned this statement about subsets into this statement about implications, and then the rest we can use what we knew from before. So let's write it up nicely. So here is our statement. A, which is the integers divisible by 6, is a subset of the integers divisible by 2, which is B. So proof. Let A and B be as stated. And this is a bit of a shortcut. So rather than writing out the definitions for A and B, again, we can just say, hey, take A and B as they're defined in the statement and assume that A is in A. Well, we know that 6 divides A because that's the definition of this set A. And so A is equal to 6k. Now, maybe we're being a little bit sloppy here and we should say where k is an integer. Okay, just maybe put in a few more words there so we're being very, very clear. Well, this implies, because it's 6 times k, we can rewrite this as 2 times 3k, and so 2 divides A. Well, that's just the definition of this set B, so we know that A is in B, which is what we needed to prove, so we've shown that A is a subset of B as required. So this is a little bit terse around here, but otherwise I think it's all pretty explicit. So maybe the only thing we should have done here is add in this little statement saying, hey, where k is some integer. Let's do something a little bit more complicated. So this one's quite a useful result. So if we take A, B, and C to be sets, if A is a subset of B and B is a subset of C, then A is a subset of C. And if you think about this, remember, this should be fairly clear. So what do we need to assume? Well, we need to assume the hypothesis here to be true. Okay, so we assume that A is a subset of B and B is a subset of C. And we know what that means. It means if something's in this first set, then it's in the second set. If something's in this set, then it's in that set. Now, what do we need to prove? Well, we need to prove that A is a subset of C. So that is, we need to prove that if X is in A, then it's in C. Well, so what do we assume here? Well, we can either assume that X is in A or not. Well, if X is in A, then since A is a subset of B, okay, that was one of our assumptions back here, if A is a subset of B, then it's in B. But because of this assumption here, since it's in B and B is a subset of C, we know that X is in C. So we've shown that if X is in A, then X is in C, which is what we need to prove. On the other hand, if X is not in A, then this implication here, the thing that we need to prove, is true because the hypothesis would be false. Okay, let's write that up. So we're going to show that A is a subset of B and B is a subset of C implies A is a subset of C. So assume that A is a subset of B and B is a subset of C. Now let X be in A. If X is in A, because A is a subset of B, we know X is in B. And similarly, if B is a subset of C, then we know that X is in C. And so A is a subset of C as required. So some of you will be thinking, well, what happened to that assumption where X is not in A? Well, that's a little bit like way back when we started proving things. Why don't we assume the hypothesis is false? Well, we don't assume the hypothesis is false because we know the implication is true by default. And so here we assume X is in A because if X isn't in A, we can't really say anything about A being a subset of C. Okay, so back over here in the previous slide where we worked out, oh, if X is in A, X is not in A, this little bit of logic here is kind of redundant. We should expect that the reader understands that, hey, well, if X isn't in A, then we can't really do anything and that implication is going to be true, but not in any useful way. So we don't have to bother proving that. So over here, we just look at what happens if X is in A, then we show that it's in C. Okay, let's do another one. So a distributive result. So if we let A, B, and C be sets, and A union B intersection C is equal to A union C intersection A union B. And so if we do some scratch work here, so let's take a look, then A union B intersection C, so we've got three sets, A, B, and C. Then A is here, B intersection C is here, and so their union is this. On the other hand, the right-hand side here, we can take A union C, that's all of this, and A union B, that's all of that, and their intersection really does look like it's going to be that. Okay, so this scratch work is just visualizing what's going on, but that's definitely not a proof. We still have to prove things. So let's only do one of the two inclusions, okay? So I'm just going to prove that the left-hand side is a subset of the right-hand side. The other inclusion, which is akin to when we're doing a biconditional, the other implication is very similar, and I'll let you do that yourselves. So we need to prove that the left-hand side is a subset of the right-hand side. And again, I'm using this very standard notation, LHS, meaning left-hand side. Okay, and I apologize for my terrible handwriting here. I really don't like writing on a tablet, especially not when I'm in the middle of recording. So LHS means left-hand side. I'm going to delete that because that looks terrible. Okay, left-hand side, right-hand side. So let X be an element of the left-hand side. Well, because it's the union of two things, we know that this means that that element X is either in A or it's in B. And so this assumption that X is in this is kind of splitting up into two cases. X is in the first set or it's in the second set. Okay, so we have two cases to consider. Assume X is in A, that is, it's in this first thing. Well, because X is in A, it's in A union whatever we want. Okay, because the union of two sets is everything in A or everything in the other set. So we can choose, because X is in A, we can choose X is in A union C, because that's one of the things we're interested in, and X is in A union B, because that's the other thing we're interested in. So because it's in A union whatever else we want. This is a very handy little bit of logic. So, well, if it's in both of these things, then it's in the right-hand side. So that's good. So then let's assume that X is in this second set, because that was our second case here. X is in B intersection C. Well, if X is in B intersection C, it's in B and it's in C. That's just what the intersection means. Well, since it's in B, again, following the same logic we used up here, it's in B union whatever else we want. So we can pick it because it's handy for us here. We can say, well, it's in B, so it's in B union A. Similarly, because it's in C, we also know it's in C union A. And because it's in both of these things, it's in the right-hand side. So in both cases, we know that X is in A union B and X is in A union C, so it's in the right-hand side. So if it's in the left-hand side, then it's in the right-hand side, which is just what we need. So all we have to do now is write it up nicely. So, the proof. Let X be in A union B B intersection C. And that means that X is in A or X is in B intersection C. And again, here we're just telling the reader, hey, we're going to do each case. So we consider each case separately. Case 1, assume X is in A. Because it's in A union whatever. So we know it's in A union B. And by the same reasoning, it's in A union C, which is just the right-hand side. So now we assume, that's our first case done. Now we assume that X is in B intersection C. So X is in B and X is in C. Well, because it's in B, we know it's in B union whatever. So it's in B union A. And similarly, because it's in C, we know it's in C union whatever. So it's in C union A. So in both cases, we know both that X is in A union B and X is in A union C. And because it's in both of these, we know it's in their intersection, which is just what we needed. And so we're done. Let's stop there.